In 1977, NASA launched 2 spacecraft on a mission that was only ever supposed to last 5 years. Voyager 1 and Voyager 2 were built to do one specific job: fly past Jupiter and Saturn, take Samwise fade into the background of space exploration history like so many missions before them. Nearly 50 years later, both of those spacecraft are still transmitting data back to Earth, still operating on technology that predates the PI. Personal computer, still traveling outward at roughly 38,000 miles per hour, and somewhere along that decades-long journey, they crossed it into a region of space so strange, so violent, and so completely different from anything scientists had predicted that it forced NASA to rewrite entire textbooks about where our solar system actually ends and what happens the moment you leave it. This is the story of what Voyager actually found out there, at the true Deej of everything we call home, and why what it detected still has scientists confused, fascinated, and honestly a little bit unsettled today. Before we get into what happened at the actual edge of the solar system, it is worth appreciating just how unlikely this entire mission was in the first place. Voyager 1 and Voyager 2 were built to take advantage of an alignment of the outer. Planets that happens only once every 175 years. A rare geometric arrangement that allowed a single spacecraft to use the gravity of one planet to slingshot itself toward the next, dramatically cutting down travel time that would otherwise have taken decades using conventional propulsion alone. Voyager 2 launched first in August of 1977, followed by Voyager 1 just weeks later in September, on a faster trajectory that would actually put it ahead of its sibling spacecraft. Voyager 1 flew past Jupiter in 1979, capturing detailed images of the planet's swirling storms and discovering active volcanoes on its moon Io, the first time volcanic activity had ever been directly observed anywhere beyond Earth. It then swung past Saturn in 1980, sending back the first close-up images of that planet's rings in stunning detail before its trajectory was deliberately bent upward out of the plane of the solar system entirely, specifically to get a close look at Saturn's largest moon, Titan. Voyager 2, following a more leisurely path, went on to become the only spacecraft in history to fly past all 4 of the outer gas giants: Jupiter, Saturn, Uranus, and Neptune, delivering humanity's only close-up look at those 2 distant ice giants to this day, decades before any follow-up mission has ever been sent back. Once those planetary flybys were complete, both spacecraft technically could have been considered finished, mission accomplished, objectives met. Instead, NASA made the decision to keep both spacecraft running, redirecting their remaining fuel, power, and instruments toward an entirely new, open-ended goal, pushing as far outward as physically possible for as long as the aging hardware could survive, to see exactly how far the sun's influence actually extended before giving way to the rest of the galaxy. Let's start with a question that sounds simple but is actually far more complicated than most people realize. Where does the solar system actually end? If you ask most people, they will probably say it ends somewhere past Pluto, or maybe out at the Oort cloud, that distant shell of icy debris theorized to surround our entire solar system. But that is not really what scientists mean when they talk about the true edge of the solar system, the boundary Voyager was actually built to reach. What they are talking about is something called the Heliopause, and understanding what that actually is changes everything about how you picture the space around us. Here is the concept in plain terms. Our sun is not just a source of light and heat. It is constantly blasting out a stream of charged particles in every direction, called the solar wind, moving at speeds that can reach over 1 million miles per hour. That solar wind inflates a massive invisible bub, hilly around our entire solar system, a protective shield called the heliosphere, and this bubble extends far beyond the orbit of every planet, far beyond Pluto, out into a region of space that took Voyager decades to actually reach. Inside that bubble, the sun is effectively in charge. Its particles, its magnetic field, its influence dominates EV, writhing. But that bubble does not go on forever. Eventually, the pressure of the solar wind weakens enough that it runs directly into the interstellar medium, the sea of charged particles and radiation drifting in the space between stars, left behind by other stars, ancient supernovae, and the broader structure of our galaxy itself. The exact boundary where the sun's influence finally gives way to that interstellar material is the heliopause, and crossing it is, in the truest possible sense, humanity's first real step out of our own solar system and into the wider galaxy. Voyager 1 became the first human-made object in history to actually cross that boundary, doing so in August of 2012, after a journey that had already lasted 35 years. Voyager 2 followed a different trajectory through T.S, a solar system, and crossed its own section of the heliopause 6 years later, in November of 2018. But long before either spacecraft actually crossed that final threshold, they were already picking up signs that something strange was happening out there, signs that did not match what scientists had spent decades predicting. The first major clue came from something called the termination shock, a point Voyager 1 crossed years before it ever reached the heliopause itself. This is the region where the solar wind, still moving at roughly 1,000,000 miles per hour, as suddenly and abruptly slows down as it starts to feel the resistance of the interstellar medium pressing back against it. Scientists had a specific prediction for what should happen here. They expected the wind to slow down significantly, but still keep moving outward at a few 100,000 miles per hour, essentially turning a corner as it felt the growing pressure of the interstellar wind. That is not what Voyager actually found. Instead, the data coming back from Voyager's instruments showed something scientists had not anticipated at all, the solar wind slowing all the way down to a full stop in outward velocity, in a region researchers ended up calling the stagnation region. The wind was not turning a corner and continuing on its way. It was essentially getting trapped, piling up against the boundary of interstellar space in a way that did not match any of the existing models. Then came an even stranger discovery, one that genuinely confused the Voyager science team for months. As Voyager 1 pushed further toward the heliopause, it entered a region scientists started calling the magnetic highway. Here is what made this region so bizarre. Normally, in the heliosphere, charged particles bounce around chaotically in every direction, effectively trapped, moving like cars stuck on local roads with no clear direction, blocked in by the sun's magnetic field lines curling around them. But in this new region, something changed dramatically. The sun's magnetic field lines, WWs, are found to be directly connected to the interstellar magnetic field lines beyond them, creating an open channel, a literal highway, that allowed lower energy particles originating from inside the heliosphere to zoom straight out into interstellar space, while higher energy particles from outside the solar system came streaming directly in. Edward Stone, the Voyager project scientist at Caltech at the time, described this moment by saying that although Voyager 1 was technically still inside the sun's environment, the spacecraft could finally taste what conditions were like on the outside, because particles were now zipping in and out along this magnetic connection like traffic finally freed from a jam. What confused scientists at first was that despite this open highway connecting the inside and outside of the solar system, the actual direction of the magnetic field lines Voyager was measuring H@E, not changed yet, which told the team that the spacecraft, despite all these dramatic shifts happening around it, was technically still inside the solar bubble. The true crossing into interstellar space was still to come, and when it finally happened, the direction of those magnetic field lines flipped, giving scientists one of their clearest signals yet that Voyager 1 had genuinely left the heliosphere behind for good. But the discoveries that came after the actual heliopause crossing are honestly the ones that changed our understanding of interstellar space the most. And one of the strangest, most talked about findings involves something scientists ended up nicknaming the Wall of Fire. Now, NGS, in that boundary region, reaching somewhere between 30,000 and 50,000 Kelvin, which converts to roughly 54,000 to 90,000 degrees Fahrenheit. Read that number again, because on paper, that sounds like it should be an impossible, catastrophic temperature for any spacecraft to survive passing through. So why is Voyager not a smoking pile of scrap metal right now, tumbling through space after getting cooked by a 50,000 degree wall of plasma? Here's the piece of physics that makes this whole discovery make sense. And it is honestly one of the most fascinating quirks of how temperature actually works in the near vacuum of space. Temperature, Re, at its core, is a measurement of how fast individual particles are moving. In the superheated boundary region, the charged particles really are moving at speeds consistent with those extreme temperatures. But temperature alone does not tell you how much actual heat gets transferred to an object sitting inside that environment. Heat transfer also depends heavily on density, on how many particles are actually colliding with an object per second. And out at the heliopause, the particle density is so incredibly low, so close to a genuine vacuum, that even though individual particles are moving at blisteringly fast, high temperature speeds, the air are simply not enough of them making contact with Voyager's hull to transfer any meaningful damaging heat. It is a bit like the difference between sticking your hand briefly into a hot oven versus dropping it into a pot of boiling water. Both might register the same temperature on the thermometer, but the water, being far denser, transfers that heat into your skin far more violently and dangerously than the air ever could. Out at the heliopause, Voyager is essentially surrounded by scorching hot particles that are simply too sparse to actually cook it. This superheated boundary layer forms specifically because the solar wind, still carrying enormous energy even after slowing down dramatically, collides directly with the interstellar gases pressing in from outside. And that collision superheats the plasma sitting right at that interface, creating a genuinely extreme thermal environment that just happens to be far too thin to be dangerous. It helps to actually picture just how empty this region of space really is, because that emptiness is the entire reason Voyager survived passing through something registering tens of thousands of degrees. In the boundary region WW here, this superheated plasma exists. You might find only a handful of particles occupying a volume of space equivalent to a small room here on Earth, compared to the roughly 10 quintillion molecules of air occupying that same volume at sea level on our own planet, individual particles moving at extreme high tempo. Tour speeds simply do not encounter Voyager's hull often enough, or with enough combined force, to transfer meaningful thermal energy into the spacecraft's structure. This is precisely why astronauts on spacewalks do not instantly freeze or burn, depending on whether they are facing toward or away from the sun, despite the enormous temperature differences between sunlit and shadowed surfaces in orbit. Temperature and heat in the near vacuum of space are simply not the same thing they are here on the surface of a planet with a thick atmosphere, and the Wall of Fire discovery ended up becoming one of the clearest, most vivid public demonstrations of that distinction that the Voyager mission has ever produced. There is one more piece of this story that deserves real attention because it involves the second spacecraft, and it turns out Voyager 2 actually had an advantage its older sibling did not. By the time Voyager 1 crossed the Heliopause back in 2012, its onboard plasma science instrument, the device specifically designed to directly measure the speed, density, and temperature of the plasma surrounding the spacecraft, had already stopped working, having failed years earlier. This meant scientists had to rely on more indirect methods, like the plasma wave measurements that eventually revealed the interstellar hum, to confirm exactly when and how Voyager 1 made its crossing. Voyager 2, however, still had a fully functioning plasma science instrument on board when it reached its own section of the Heliopause in November of 2018, 6 years after its sibling. This gave researchers something genuinely valuable, a direct, real-time confirmation of the sudden changes happening as the spacecraft crossed the boundary, rather than having to piece the story together after the fact through secondary measurements. Voyager 2's instruments recorded an abrupt jump in plasma density and a corresponding drop in the speed and temperature of the surrounding particles, right at the moment of crossing, providing scientists with the clearest, most direct, real-time confirmation yet of exactly what happens physically at that boundary. And because Voyager 2 crossed the Heliopause at a completely different location than Voyager 1, entering interstellar space from a different angle relative to the Sun, its data gave us scientists their first real opportunity to compare two separate crossing points directly, confirming that the strange, irregular, farther than predicted shape of the heliosphere was not simply a fluke of Voyager 1's particular trajectory, but a genuine, consistent feature of how our Sun's protective bubble actually interacts with the surrounding galaxy from multiple directions at once. Alongside that startling temperature discovery, Voyager also detected something about the magnetic environment out there that scientists had not fully anticipated either. The spacecraft picked up magnetic field lines in the interstellar medium that appeared noticeably stronger, and more orderly than researchers had predicted going into this mission. That single finding carries a surprisingly big implication. It suggests that the magnetic pressure coming from interstellar space, pressing in against our solar system's protective heliosphere bubble from the outside, might be significantly stronger than scientists had modeled beforehand. Think of the heliosphere as a giant sun-powered bubble holding back the rest of the galaxy, and think of this discovery as evidence that whatever's on the outside pressing back against that bubble is pushing harder than anyone expected. That single data point alone forced researchers to reconsider models of how our entire solar system interacts with and is shaped by the broader galactic environment surrounding it. And then there's the discovery that might be the single strangest, most quietly beautiful thing Voyager has ever detected. Something scientists ended up calling the interstellar hum. This one came from Voyager's plasma wave system, an instrument originally designed to detect and measure oscillations in charged particle density around the spacecraft. For most of its operational life, this instrument mainly picked up dramatic, short-lived bursts of activity, plasma oscillations, triggered specifically by outbursts from our own sun, solar storms, and coronal mass ejections that sent shockwaves rippling all the way out through the solar system and into interstellar space itself. Hers described these solar-triggered events almost like sudden bursts of lightning inside a thunderstorm, loud, dramatic, and relatively brief. But once Voyager 1 was firmly established out in interstellar space, Cornell University's researchers led by doctoral student Stella Koch-Ocker discovered something running constantly in the background, underneath those occasional solar-triggered bursts. A faint, persistent monotone signal, a genuine, continuous hum coming from the interstellar medium itself. Ocker described the discovery as detecting the faint, persistent hum of interstellar gas, explaining that it was very faint and monotone, specifically because it existed within an extremely narrow frequency bandwidth. Cornell astronomy professor James Cordes offered one of the most memorable descriptions of the phenomenon, comparing the constant background hum to the sound of a gentle, quiet rain, with the occasional dramatic solar outburst representing a sudden burst of thunder and lightning within that steady rainfall before everything settles back down into that same faint, continuous hum. This was not something scientists went looking for specifically. It was discovered almost by accident, buried inside data that Voyager had been transmitting back across more than 14 billion miles of space, and it turned out to be an entirely new way of directly measuring the density of the plasma making up interstellar space itself, a measurement scientists previously could only estimate indirectly. This hum connects directly to one of the most dramatic and long-running discoveries to come out of the Voyager mission, something researchers nicknamed tsunami waves. Here is how these form. When our sun experiences a coronal mass ejection, violently hurling a massive cloud of magnetized plasma outward from its surface, that eruption generates an enormous pressure wave that propagates outward through the entire solar system, eventually slamming into the interstellar plasma sitting beyond the heliopause. When that pressure wave collides with the interstellar medium, it creates a genuine shock wave, and that shock wave causes the surrounding ionized gas to resonate, to essentially ring like a bell, vibrating at frequencies Voyager's instruments could actually detect and measure from over 14 billion miles away. Voyager has now experienced at least 3 of these tsunami waves since crossing into interstellar space, and remarkably, the most recent one, first detected in February of 2014, was found to still be propagating outward years later, making it the longest-lasting shockwave scientists have ever observed moving through interstellar space. Don Gurnett, a physics professor at the University of Iowa who worked extensively on this research, noted that most researchers going into this mission assumed the interstellar medium would turn out to be relatively smooth and quiet. Instead, these shockwaves turned out to be far more common than anyone anticipated, and each one gave scientists another opportunity to indirectly measure the density of the plasma surrounding the spacecraft, because denser plasma rings at a noticeably higher frequency than sparse plasma does, functioning almost like a bell made of interstellar gas that changes its pitch depending on exactly how much material it is made of. Each new tsunami wave detection also gave researchers back on Earth an independent way to confirm the plasma density readings coming from Voyager's other instruments, and the trend those readings revealed turned out to be its own quietly important discovery. Analysis of Voyager's density measurements showed a significant, sustained rise beginning around 2013, climb, to a notably higher and more stable level by around the middle of 2015, a pattern entirely consistent with what scientists would expect if the spacecraft had genuinely left the turbulent, variable environment of the heliosphere behind and entered the comparatively steadier, denser plasma of true interstellar space. This saint. ED climb and measured density became one of the most persuasive independent lines of evidence, confirming that Voyager 1 really had crossed over into a fundamentally different physical environment, corroborating the more dramatic, headline-grabbing discoveries like the wall of fire and the interstellar hum with a slower, quieter, but equally rigorous body of supporting data. One of the most consequential discoveries of the entire mission, though, is not about temperature or magnetic fields or mysterious humming sounds. It is about location. Scientists had built detailed models over decades attempting to predict exactly how far away the heliopause should actually be, based on our understanding of solar wind pressure and the density of the surrounding interstellar medium. When Voyager 1 finally crossed that boundary, the actual measured distance came in significantly farther out than nearly every prediction had suggested, with some analyses placing the true crossing point roughly 2.4 billion miles beyond where existing models expected it to be. That is not a small margin of error. That is an enormous discrepancy, and it forced an uncomfortable but scientifically important realization that our theoretical understanding of how the sun's protective bubble interacts with the wider galaxy was significantly less precise than researchers had believed. The shape of the heliosphere itself turned out to be different from predictions as well. Not a perfectly smooth, symmetrical bubble, as many models assumed, but something far more complex and irregular, shaped by the constantly shifting pressure of both the solar wind pushing outward and the interstellar medium pressing back in from the surrounding galaxy. What makes all of these discoveries even more remarkable is the technology actually responsible for making them. Voyager 1 and Voyager 2 were both built using computer technology from the mid-1970s, decades before the smartphone in your pocket existed, decades before the personal computer became a household item. Both spacecraft are powered by radioisotope thermoelectric generators, devices that convert the heat produced by the natural decay of plutonium into usable electricity, and that power source has been slowly, steadily weakening for nearly 50 straight years, forcing NASA engineers to make increasingly difficult decisions about which instruments to keep running and which to shut down permanently in order to conserve, power to keep the spacecraft transmitting data at all. And yet, against every reasonable expectation for hardware built in that era, both spacecraft are still out there right now, still gathering and transmitting genuinely groundbreaking scientific data from a region of space no other human-made object has ever directly sampled. Both spacecraft are also carrying something that has nothing to do with scientific instrumentation at all, something that exists purely as a message, a time capsule aimed not at scientists back on Earth, but at whoever or whatever might one day encounter these spacecraft drifting through the emptiness of interspace. Eller space, long after human civilization itself has changed beyond recognition or ceased to exist entirely. Bolted to the side of each Voyager, spacecraft is a golden phonograph record, containing a carefully curated collection of sounds and images meant to represent the full diversity of life and culture on Earth. Greetings, recorded in dozens of different human languages. U-ages, the natural sounds of wind, rain, thunder, and ocean waves. Music spanning an enormous range of cultures and historical periods. Photographs depicting human anatomy, family life, cities, landscapes, and technology. Instructions etched directly onto the record's cover explain, using purely mathematical and scientific symbols rather than any specific human language, exactly how it should be played, on the small chance that whoever eventually finds it possesses no shared frame of reference with humanity at all. Those two golden records are now traveling through interstellar space at roughly 38,000 miles per hour, carrying a message that will likely outlast the sun itself, drifting silently through the same faint interstellar hum that Voyager's instruments first detected decades after launch, on a journey with no planned destination and no expected recipient. The record itself was assembled under the direction of a committee chaired by the astronomer Carl Sagan, who understood from the very beginning that the odds of this message ever actually being found, and understood by another intelligent civilization, were astronomically small, given the sheer emptiness of interstellar space and the immense timescales involved. Voyager 1 is not currently heading toward any particular star system, and even at its current speed, it would take tens of thousands of years just to cover a distance comparable to the gap between our sun and its nearest stellar neighbor. But Sagan and his team decided that the attempt itself was worth making regardless, describing the record as a message sent across an ocean of space and time, less a practical communication device and more a kind of cosmic gesture, a statement that humanity existed, that it once looked outward, and that it tried to say something meaningful about itself to whatever might be listening. The record also includes a diagram indicating Earth's position relative to a set of pulsars, rapidly spinning neutron stars that emit radiation at extremely precise, predictable intervals, giving any future finder a genuine, calculable roadmap back to the exact location and time period the record was launched from, encoded entirely in physics and mathematics rather than any spoken or written human language. So what does all of this actually mean? Beyond simply being a fascinating collection of scientific trivia about two aging spacecraft, it means that everything scientists thought they understood about the true edge of our solar system, going into this mission decades ago, turned out to be incomplete in almost every meaningful way. The boundary was located much farther out than predicted. Its shape was more irregular and complex than expected. The temperature at that boundary reached genuinely extreme, superheated levels that only avoid being catastrophic because of how thin that superheated plasma actually is. The magnetic environment beyond the heliosphere turned out to be stronger and more structured than anticipated, suggesting the pressure pushing back against our sun's protective bubble from the surrounding galaxy is more intense than researchers had modeled. And underneath all of those dramatic, individually surprising discoveries, there is a constant, faint, barely perceptible hum, running continuously through the space between stars, occasionally interrupted by tsunami-sized shockwaves triggered by activity happening back on our own sun, waves that can keep rippling outward and ringing through interstellar plasma for years after they were first generated. Every one of these discoveries came from spacecraft that were only ever designed and funded for a 5-year mission to photograph Jupiter and Saturn. Nobody involved in building Voyager 1 and Voyager 2 in the 1970s expected these machines to still be operating, transmitting genuinely novel scientific data nearly half a century later from a regional F-space that did not even have a confirmed, universally agreed upon boundary until Voyager itself finally reached it and measured it directly. And as both spacecraft continue drifting outward, their POE are slowly fading, their instruments being shut down one by one to conserve what little electricity remains, they continue sending back faint radio signals across a gap of more than 14 billion miles, still teaching us, decade after decade, that the true edge of our solar system is far stranger, far more dynamic, and far less understood than anyone ever expected it to be. Millions of miles further along its outward path. A command sent from Mission Control takes another full day to reach the spacecraft in return, meaning any single question and answer exchange with Voyager 1 now takes roughly 2 full days from start to finish. Engineers working on the Uno E-mission today are, in a very real sense, operating equipment that most of their own colleagues were not yet born when it launched, relying on documentation, programming languages, and hardware architecture that has become almost archaeological in nature, simply to keep 2 of humanity's most far-flung achievements alive for a few more years, or if we are fortunate, a few more decades. NASA has had to make increasingly difficult choices about which scientific instruments to keep powered on each spacecraft, as their plutonium power sources continue their slow, inevitable decline, understanding that every instrument shut down to consi. Our electricity is a door quietly closing on some future discovery the team will simply never get to make. Engineers have gone so far as to power down heaters protecting instruments that were never designed to survive the extreme cold of deep space without them, essentially gambling that decades-old components will keep functioning even after losing the thermal protection they were originally built to require, purely because the alternative is running out of power to operate at all far sooner than necessary. Every one of these decisions buys a little more time, a little more data, a little more insight into a region of the universe that remains almost entirely unexplored by any other means available to us. Even once both spacecraft eventually run out of power entirely, likely sometime in the coming years, they will not stop moving. They will continue drifting outward silently, forever, carrying their golden records and the last data they ever transmitted, long after every human being currently alive has died, long after the civilization that built them has changed in ways impossible to predict. NASA has occasionally discussed potential future missions, specifically designed to follow in Voyager's path, purpose-built interstellar probes carrying modern instruments capable of measuring the boundary of our solar system with far greater precision and for far longer than either aging Voyager spacecraft can manage today. But no such mission has actually launched yet, which means, for the foreseeable future, everything we know directly about the true edge of our solar system, the superheated plasma, the unexpectedly strong magnetic fields, the persistent interstellar hum, the tsunami waves still rippling outward years after they first formed, continues to come from 2 machines built with less computing power than a modern calculator, launched during a decade when disco was still on the radio. And that, ultimately, is what makes the story of what Voyager detected at the edge of the solar system so much bigger than any single discovery about temperature or magnetic fields or faint interstellar hum. It is the story of 2 machines built with less computing power than a modern calculator, launched during a decade when disco was still on the radio, that ended up rewriting our understanding of where our solar system truly ends and what the wider galaxy actually feels like once you finally leave it behind. Every model, every prediction, every carefully constructed theory scientists carried into this mission got tested directly against real measurements taken 14 billion miles from home, and in discovery after discovery, reality turned out to be stranger, more dynamic, and more surprising than anything anyone had modeled on paper beforehand. Somewhere out there right now, 2 golden records are drifting further into that same strange darkness, carrying the sound of Earth's rain, the sound of human laughter, and the faint hum of interstellar gas, all traveling together into a future none of us will ever get to see for ourselves.